Hey everyone, welcome back to my Calculus 2 series. In today's lesson, we're going to be going over volumes. So for this lesson, there's going to be quite a bit of sketching and drawing, and I do apologize in advance. I'm not an artist, but I will try and do my best to draw shapes in 3D. So let's pretend that we've got this shape right here in green, and it's a 3D shape, even though it might not look like it. Now it does look like some sort of vase flipped on its side. Basically, the way we are going to approach solving volumes is by taking these sheets that I've drawn, or planes, and kind of making an intersection with our solid. I want to introduce the topic of cross sections, and basically this right here would be a cross section. Also, this right here would be one, and this right here too. So all three of these planes would be cross sections, and essentially a cross section is just an intersection of a plane with our shape. Now these cross sections can be thought of as slices, and I encourage you to think of them as so. Now as you can see in the picture, we have drawn very thin slices. However, when we're going to be approaching volumes, what we're going to do is we're also going to think about the thickness of each slice. So if you remember back in the area under a curve video, what we did was we kind of split up the total area into smaller areas that were known. So we're going to apply the same concept to find the volume of these 3D shapes. So essentially, if you think about it, what a volume is, it's the area of something, right? And then we also want to multiply it by let's say the thickness. So let's look at this cross section right here. I'm going to outline in black, and this essentially is an intersection of our plane with the solid. And what we want to do is, if we know the area of this, let's say this is actually, I'm going to write it out here. Let's say the area of this little cross section is a of x, right? Well, if we want to find the volume of that, all we need to do is consider how thick is this slice right here, right? If this slice were to be super thick like this, right? If it were to be something like that, well then the volume of that slice would be a of x, meaning that area, times however thick this would become, right? However, whatever the thickness would be on this. So in that case, the thickness we'll call delta x, meaning this would be delta x. Now here is the volume, the formula of the volume for a single cross section. However, the same thing applies as what we did in the area tutorial, and basically what we need to do is we need to sum up all of these areas. So to kind of break it down a little bit further, a at xi is going to be the area of the ith slice, and then delta x is going to be the thickness. Now what we want to do is we want to take this formula, which is the volume of one specific cross section, and we want to sum it up, and we essentially know how to do that already. We want to sum it up by using the summation formula from I equals 1 to n, and then we want to sum up all of the volumes which are expressed like this, and then this formula right here, well, this will give us the total volume, the entire volume of the shape. So here is the official definition of volume. So we let S be a solid that lies in between x equals a and x equals b. Relating it back to our image, x equals a might be somewhere here, right? These are kinds of the starts and ends of where this solid is. So this might be, let's say x equals b, and then this would be x equals a. So the solid lies in between those two x value extremes. And then if the cross-sectional area of S, meaning the solid, in the plane being like the these little red planes right here, through x and perpendicular to the x-axis, as you can see, I've drawn all the planes perpendicular to the x-axis, and the area of that cross-section that develops between the plane and the solid is a of x. So it's an arbitrary area of this shape right here. Whatever this cross-sectional shape will be, in this case there are going to be circles or ovals. Whatever the shape of that cross-sectional area will be, we'll call it a of x, and then a obviously must be a continuous function. Then we say that the volume of the entire shape is equal to the limit as n approaches infinity of this sum, which we derived up here, right here. And the reason we want to take the limit as n approaches infinity, it's for a similar reason as we did in the area video. It's because we want the most amount of cross sections, meaning we'll have the most amount of these kind of like slices, and then we want to sum up all those slices. But in order to get a very accurate representation of what the true volume is, we want there to be as many slices as possible. And obviously we can transform this limit and sigma notation into an integral notation, and it's going to be written like this. Basically, again, these are our bounds of integration, and then what we want to do is we want to take the integral of the area of like the ith cross section, and then obviously in this case delta x was the width of that slice. In this case it will be dx. So now I'll be going through a series of examples, and basically I suggest you revisit these if you haven't picked the concept up yet, but each example is going to be something different, so just pay pretty close attention. So here is our first example. Find the volume of the solid obtained from rotating the region under the curve y equals the square root of x from 0 to 1 about the x-axis. So my suggestion to you is that first we draw out a 2D sketch of what these bounds sort of tell us. This, and then about the x-axis. So we'll kind of draw everything out, visualize it, and then we'll move on. So there we go. We have drawn the figure. So in green, this is going to be y equals f of x, and f of x being the square root of x. So this function right here. And obviously I have labeled from 0 to 1 in red. So as you can see, this endpoint, and then I've labeled the x with this dotted line, and then we want to rotate this about the x-axis. So what does that mean? Basically what we're going to be doing is we're going to be taking the shape and rotating it like this around the x-axis. Pretend this kind of like goes through here, but we're going to be rotating it around that x-axis. And what I suggest you do to solve these problems is kind of draw yourself what the 3D shape might look like. So there we go. I have drawn what the 3D shape will look like after we have rotated it about the x-axis. Now as you can see, I've also drawn a little cross section right here that we might draw. It'll kind of make it useful for us to see what a cross section might look like and how we can compute the area of that, right? So in this case, it's going to be just a little like, it's going to be an oval. So something maybe like this. Again, I apologize for the drawing, but it'll be an oval, and then it'll have a thickness. So that oval, we don't know what that thickness is, but in this case, we're going to say that the thickness of this oval, well, that's delta x, because we are alongside the x-axis right here. Now, if we look closely, that shape of the cross section, well, it's just an oval, or in this case it's actually going to be a circle, because it's going to be like an even rotation right across the x-axis. So we know how to find the area of a circle, right? So the area of the cross section a of x, well, that's just going to equal to pi r squared, right? In this case, pi is a constant, so it's okay to keep, but what is r in this case, right? If we look at it, the radius spans from this x-axis all the way upwards to the kind of outermost edge or outside edge of this circle, right? And what is that x? Well, in this case, we can compute that value because it's right at the endpoint, but in this case, it would be up here, right? And as you can see, this radius goes towards the edge of this function right here. So this function edge right here that I'm going to label in black, that is the outer edge of that radius. That's actually going to tell us how high the radius is, right? So if we calculate the value of y at all these points, well, it's just going to tell us the radius at that x value. So we want to express this generally, right? So at any given x, what is the radius? Well, it's the y coordinate of the function square root of x, which happens to be the one that they gave us. And obviously we're going to keep that squared. Now it's pretty easy. We have the area, and all that's left to do is to take the integral from the bounds. And the bounds were given to us in the question. It was 0 to 1. So we take the integral from 0 to 1 of a of x dx, and then we are simply just going to substitute what a of x is. It's going to be pi square root of x squared dx. Obviously, you can simplify that even further to just the integral of, I'm going to bring pi outside, and then this is just going to be x dx, and it's pretty simple from here. I'm going to speed it up. You've seen this integral plenty of times. And there you go. That is going to be the volume of this kind of ham-looking shape right here. So now moving on to the next example, it's asking us to find the volume of the solid obtained by rotating the bounded region, or sorry, the region bounded by y equals x cubed, y equals 8, and x equals 0 about the y-axis this time. So no longer the x-axis. So let's go ahead and plot out the 2D graph first. So there you go. I have drawn out the 2D graph, and this is what it's going to look like. So this function in green is y equals x cubed, and these red dotted lines represent the bounds that were given right here. So y equals 8 and x equals 0. So that's what these red lines are. And the question is asking us to rotate this about the y-axis. So we know that this is the y-axis, and essentially we're going to be taking this function and rotating it like this, 360 degrees around the y-axis. So now we might as well draw a little sketch of how we think the function will look. So there you go. I have drawn what this function might look, and as we can see, it still looks like that like ham kind of shape, but now it's flipped. Instead of in this question we had it kind of sideways, now we kind of flip it 90 degrees. So it's the same kind of shape. We know how to solve this problem, and maybe this is a little more clear, but I've drawn the cross section over here, and you can see it's kind of like this dish sort of shape. It's just like a circle, and then it has some sort of thickness to it. And obviously that thickness, we're going to label it. But in this problem, we're going to label it delta y. And the reason that is because now this change, this thickness is in the y-axis, right? We're no longer going along the x-axis, it's along the y-axis. So we're going to label this delta y. And again, this is going to be a circle, even though it might not look like in my sketch, and I apologize for that, but it's going to be a circle. And we know how to find the area of this cross section because, well, it's a circle, so it's just going to be pi r squared. And what is the radius in this case? Well, in this case, the radius goes from here all the way to the edge. And in this case, the edge is going to be just the x value, right? So it's going to be just the x value. In this case, it's going to be up here. If we were to look at the radius of the topmost part, well, it's just going to be the x value here, right? And all we're going to write for now is just x squared. So now that we have found, in a sense, we have found the area of these cross sections, what we want to do is now we want to kind of sum them up using the integral. And we can do that by taking a look at the bounds. So firstly, one thing we can notice is that we will no longer be integrating in terms of x. And the biggest giveaway is this delta y. So we know that this is going to be, sorry, not delta y, it'll be dy, right? But we don't know, this is still going to be a of x, but we don't exactly know what this function will look like. We have a rough idea, it'll be something like this, but we know we'll need to get rid of this x variable eventually because we're integrating with respect to y. So that means that our bounds also have to be with respect to y. And we can see that this function kind of spans from y equals 0 all the way to y equals 8. So the bounds of integration will be from 0 to 8. Now we need to deal with this function. Before a of x used to be pi x squared, and then we would have dy. However, we know that we can't have this x value in here because we'll be integrating with respect to y. So we need to figure out a way to kind of get rid of this x value and sub it in for a more meaningful expression in terms of y. But how can we do that? Well, we have this expression up here, and what we can do is we can actually solve for x. What is x going to equal? Well, in this case, x is going to equal the cube root of y. And there we go. Now we can see that we have an expression in terms of y that is equal to x. So we can straight up sub this into here, and we'll get a perfectly good integral. There we go. There is our final integral to calculate the volume of this ham shape. And I'm just going to go ahead and zoom through this because I'm sure you've seen this integral plenty of times and I'm sure you know how to do it by now. There we go. There is our answer for this volume of this ham looking shape over here. On to the third example, the question asks us, the region R enclosed by the area, by the curves y equals x and y equals x squared is rotated about the x-axis. Find the volume. So like usual, we are going to start off with a 2D sketch of both of these functions. There we go. I have sketched both of these functions. Obviously in blue is y equals x because it's a linear function, and in green we have y equals x squared. Now we can note the points of intersection between these two curves. One of them will be 1, 1, and then over here will be 0, 0. So now we are asked to rotate this about the x-axis. The x-axis is here, meaning we'll be rotating like this. Now it's time to draw the 3D sketch of what this function will look like. There we go. I have drawn the 3D sketch of what this shape will look like after we rotate it. And essentially, it's going to look like a cone because of this outer flat edge right here, the blue one, so y equals x. However, it will have a hollow interior because as we rotate this little slice right there that we see that is formed by the two curves, it's not entirely full like we had with these functions. So as you could see over here, the function takes up the entirety of the space here. However, when we have this little slice and we're rotating it about the x-axis, well, all of this area right here is not going to be covered, and it's going to end up just hollow when we rotate about the x-axis. Now, as we can note, I have also drawn a little cross-section over here, and essentially it's still going to look like a disc. However, it's just going to have a hollowed out center. Now, one thing we can note, the thickness of that disc is going to be labeled delta x because, again, we are along the x-axis. Therefore, it will have a thickness of delta x. Now we can go on to compute what the area of this kind of hollowed out circle will be. So if we take a sort of bird's eye view of this, the hollowed out circle will look something like this. It will have a small circle inside of it, and then it'll have a bigger circle, almost like a CD. And the way we can compute the area, so all of this region of this kind of CD-like shape is, well, if we have this middle point, what we can do is we can take the area of this large circle. I should label this in red probably so you guys can see. We can take the area of this large circle by taking this radius, and then we can subtract it by the area of the small circle, taking that other radius. So in a sense, what we're going to have is, so the area of the outer circle is going to be given by pi times the radius of the outer. I'm going to label this RO squared, and then we're going to take away the area of the smaller circle. So the radius of the smaller one is going to be RI, meaning R inner squared. This right here, this formula will give us the area of this disc-like shape. Now we can apply the same thing over here and just apply this formula. So it's going to be pi times the outer radius. And in this case, we can see that the outer radius, if we were to start here, the outer radius is going to be the height of this blue function. And the blue function happens to be y equals x. So the height of it would mean, we're talking along this side, the height here. So it would be the y coordinate. And we can kind of know that we're going to plug in some sort of x value into here because we are going to be integrating with respect to x. And again, the thickness over here, this delta x, tells us that we need to have x variables in our function. So the height of that function is given by y, and y equals x. So I'm going to be plugging x into here. Now we want to subtract the area of the smaller circle, meaning the inner one, or this green one right here. And the way we can do that, well, that radius is only going to be up to here. And how can we compute that? Well, that is, in a sense, the height of this green function. And the height of this green function is given by y, and y is given by x squared. So I'm going to plug in x squared here, squared. Now I can go on to simplify this and say that it's pi x squared minus x4. And there we go. We have computed the area of an arbitrary cross section. All that's left to do is to sum up all of the areas by using the integral. The last thing that we want to do is figure out the bounds of integration. Now we know that because we're taking dx over here, or delta x, we know that our bounds are going to be in terms of x. So what are they? Well, this solid starts from x equals 0 here, and it ends right here at x equals 1. And we know that because this is the point of intersection. So our bounds will be from 0 to x equals 1. And we want to integrate the area of the ith cross section. So in this case, it will be pi x squared minus x dx. And again, I'm sure you guys have seen very similar integrals, so I'm just going to fast forward through the solution of this integral. So there you go, we have solved for the volume of this hollowed out cone. One little quick note that I want to give is that we're going to be using this formula right here to find the area for hollowed out shapes. So this is pretty important to remember. All it is that we want to find basically the area of both circles. This right here is the area of the outer circle, meaning the biggest one, and we want to subtract the area of the inner circle. So in the case over here, the outer radius will span from the center all the way to the outer side, and then the inner circle, well, that's just going to span to here, and that's it. All we want to do is we want to subtract these two areas to basically find the leftover area, which is going to be all of this. However, for solid shapes, we don't need to subtract this inner circle because there's no inner circle, and we can simply get away with using the formula A equals pi r squared. So now for the last example, we're asked to find the volume obtained by rotating the region bounded by x equals the square root of y, x equals y, about the line x equals 1. So in previous examples, we were rotating about either the y-axis or the x-axis. However, in this case, we are asked to rotate it about this line x equals 1. And notice here, I've labeled this x2 and x1 just so that we don't get confused which x value we are talking about. So like usual, the first step is to draw a 2D sketch of what this function will look like. So there you go. I have drawn a quick 2D sketch of how this area will look like when these two functions are combined onto a graph. So this green function right here is the x equals the square root of y. And the blue graph right here is the x equals y graph. Now, again, these are the same exact functions from last example, so they will have the same points of intersection being 0, 0 and 1, 1. However, I've also included this line x equals minus 1 because we are told to rotate about it. And what that will mean is that we will be rotating this area around this x equals minus 1 line. Now the next thing to do is to draw a quick 3D sketch of what this shape will look like when rotated. So there you go. There's a quick little sketch of what the function, or sorry, what the shape will look like when rotated. Again, sorry, I'm not an artist. I'm not really good at drawing. And as we can see, I've labeled over here a quick little cross section. We could see that the thickness will be over here, and this will be labeled as delta y. Again, this is because we're along the y-axis. Now, to find the area of the cross-section given over here, we know that we can apply this formula that we have just learned because it is a hollowed-out shape. So it will be pi times the radius of the outer radius squared minus pi times the inner radius squared, basically subtracting the two areas of the circle. So now the outer radius is given from the center of the circle all the way to this green edge. And it's given by the x value, as we can see here. So what is that x value? Well, the x value is given by the green function, and the green function happens to be x equals the square root of y, right? So it's nicely formatted for us. We already know what the x value is because the function literally is x equals the square root of y. So the square root of y tells us what the x value is. However, we also need to compensate for this little shift right here. Because we are no longer rotating along a axis, we are rotating about another line over here. We need to account that we have shifted one total unit. So the radius is no longer just this x value. This x value is given to us by the function. However, we also need to add on this extra 1 because we have shifted that line. So the total outer radius will be 1 plus x, but x is given to us by the square root of y squared minus pi. And now it's time to figure out the inner radius. Well, the inner radius will span from the center of the circle all the way to this blue edge right here. And the blue edge right here is given to us by the function x equals y. And again, we are looking for the radius is right here. So this is x again, and that is given to us by y. But once again, we need to account for this shift right here. So it'll be 1 plus y squared. I can go on to simplify this really quick and say that it's just 1 plus the square root of y squared plus, or sorry, minus 1 plus y squared. Now all that's left to do is to sum up all of these cross sections using the integral. So we're going to write the integral, and now we need to figure out the bounds of integration. So because we have chosen dy to be our thickness, that means that our bounds of integration are going to be along the y-axis. Now we need to figure out, where does this function span on from the y-axis? Well, we can see it spans on from 0 all the way to this top value is given to us by this point of intersection right here, because this is the maximum value where the function kind of cuts off and the area is sort of cut off. The y value of this coordinate is going to be 1. So we know that this function spans from y equals 0 to y equals 1. Therefore, our bounds of integration are going to be from 0 to 1. And we want to sum up the area, which is given to us by pi, 1 plus the square root of, y squared minus 1 plus y squared. And we want to integrate with respect to dy. Now I'm going to fast forward through this integral solution, because again, I'm sure you've seen many integrals like this. So there you go. We have figured out the area of this sort of like bowl-shaped thing. So that's it for today's lesson on volumes. Essentially, the process to finding these volumes is the same. We kind of draw them out. We draw what the 3D shape will look like, find a cross-section, and then we just want to find the area of that cross-section. We want to find the bounds of where that shape spans on, and then we simply want to integrate, and the integrals are usually pretty simple for this kind of stuff. It's just the process to find the area of the cross-section. If this video has helped you out at all, please leave a like and comment as to what it helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I will catch you guys in another video.